Error handling in Go is a bit of a hot topic. Some people love it and some people hate it with a fiery passion. But even if you're one of those unreasonable people, knowing how to work with errors in Go is super important. And as you'll see in this video, really not that hard. So let's get started. The first and most defining feature of errors in Go is that they are a built-in type. Specifically, an error is an interface type defined by the Go language. And the error interface defines a single method called error that returns a string, which will be the error message. And because errors are defined as just a regular type, you can use them in the exact same way you would use other types like ints and booleans. And that means there's no concept of throwing an error like there is in languages like JavaScript. Instead, you need to return errors from functions the same way you would with any other type. There are a few variations on how errors are created in Go, with the first being a basic error that you create directly. And there are two common ways that you can create basic errors. The first is using errors.New, which accepts the error message. So this function will return a new error where the error method on the error interface will return the error message that you pass in. And one important thing to note is that this returns a pointer to an internal error type defined in the standard library source code. And I'll cover the actual definition and that code in a bit. There are also a few conventions you should know when you're creating errors. First, you should use pointers whenever you can for all of your error values. And second, your error message should be lowercase with no punctuation at the end of the message. Okay, the second way to create a basic error is using fmt.errorf. This does the exact same thing as errors.new, but it also lets you format the string. So if we want, we could pass in a user ID here using the fmt string formatting. And all of the verbs you can use for string formatting are covered in the fmt docs, which I'll leave a link to in the description. And I might do a video on that in the future, so subscribe if you want to stay updated. So that's how you make basic errors. But because error is just an interface, it's really easy to make custom error types. We just need a struct with any custom properties that you want on your error. Then we'll add an error method that implements the error interface. And so with custom errors, you can use the custom properties in the error message that gets printed from the error method. And using the new error type is super straightforward. We just create a new pointer to stick with the pointer convention and pass in the values. And then when we print that error, the error method gets called and this error message will be printed out. So that covers basic one-off errors and custom errors. But a lot of the actual errors you'll be using are something called Sentinel errors. And all they are is literally just package level error variables. These are super useful when you have a specific known error that you need to look for. So for example, we could use our error not found Sentinel error when you're trying to find a user in a database and you can't find them. The biggest benefit of Sentinel errors is that it works across package boundaries. So Sentinel errors are used a ton in the standard library. So when you're working with a package from the standard library or elsewhere, you should look to see if it exposes any Sentinel errors. And one more thing is that by convention, the name of Sentinel errors should start with error, which is important when we start talking about control signals. Now, as a reminder, errors are literally just a type that has an error method attached. So it's easy to use an error type to pass information other than an actual error. For example, the IO package has a Sentinel error called end of file. And this technically isn't a real error because it's expected behavior when you're reading a file. But it does signal that you need to stop reading that file. So instead of errors, these are called control signals. And when it's a package level variable like this, it's called a Sentinel value instead of a Sentinel error. And this is why it's important to have your actual Sentinel errors start with error. So the consumer knows that this is an unexpected error and not just normal behavior. When I first learned this, it really felt like we were splitting hairs, but there's a good reason to do this. So let's say I have a function that returns an error, but it could also return a control signal like end of file. And I'll just mock it up quick for demonstration. So we have two cases. The first, if we fail, and then we return an actual error. And the second, if we hit the end of file, in which case we return the control signal. If you used a non-error type for the control signal, then you would have to have a separate control signal type that you returned, which gets super confusing and noisy. So instead, we make the control signal an error type, and then we have only one return parameter. So control signals effectively piggyback off of the error interface. These are also usually done as Sentinel values, but they don't need to be. You could just as easily have a custom error type if you need more information than just a message or the actual type. Okay, so outside basic errors, custom errors, and Sentinel errors, you can also use wrapped errors. And they're used when you want to add context or another error on top of an existing error. So let's say we have a function that just returns an error. And in this case, it literally always returns an error. Then let's say we have an outer function that will call our error function. If an error happens in the wrapped error function, then we'll want to return that as well as any errors that happened in the deeper function. So we'll need to wrap this nested error in another error. And it's super easy to do. You use the same errorf function from the FMT package. And when we format the string, we're going to use %w, which stands for wrapped, and then pass the nested error in. So we'll return the outer error. And now we can get the wrapped error by calling the function. And to drive the point home, we can wrap the error again using the same fmt.errorf with the same type of format string. And now when we print this and then run the code, you get the outer error message followed by the next one in and then the deepest one. So it basically just builds them up on top of each other. So outside of wrapping, you can also join errors together. And it has a slightly different use case than wrapping. Wrapping is used when you want to add context or another error on top of errors that happened deeper in the call chain. But joining is used when you have two or more independent errors that happened on the same level. So if I have a basic function that returns an error, and then I have another function that does the exact same thing, and I want to record both of those in a single error value. So we have the first error and the second error. Then I can use the errors.Join method and pass in the two errors I want to join together. And if you want, you can also use fmt.errorf and pass in more than one error using the %w. Then we can print those. And when I run it, you can see that the joined errors combine the error messages that were passed in. So that is a lot of ways to create errors. And when I was learning, I found all of this super confusing, but reading the source code clears it up a bunch. So next, I'll go over the internal structs that are used to represent errors when you use the different ways you can to create errors. First, a basic error returned by errors.new. Internally, it uses a super simple struct with one property. And the error method implementation is also pretty straightforward. It just returns E.S. So this is as dead simple as it gets, just a struct with a string. But errors created with the errors.Join function work a little bit differently. So this function returns a type called join error, and it's also a struct, but instead of having a single string property, it has a slice of errors. It also has a more complex error method that I won't bother retyping out. But the gist of this is that it builds a new error message string using the error messages from each of the errors you're joining, with each message separated by a new line. And it also implements an unwrap method that just returns the slice of errors held in the struct. Now, errors returned by fmt.errorf is where I was most confused about all this, because there are two different cases. First, if you only wrap a single error using 1%w, then you'll get a wrap error type, which holds the fully formatted error string and the nested error value that you passed into errorf. This one also has a super simple error method where it just returns the fully formatted string, but implements a slightly different unwrap method that returns the nested error. So this returns a single error instead of an error slice, which will be important when I go over what you can do with these error types in a bit. Now, if you join errors using errorf with multiple %w's and errors passed in, then instead of a wrap error, you'll get a wrap errors type. And this again has the fully formatted string, but instead of a single nested error, it has a slice of nested errors. Again, the error method implementation just returns the string, and unwrap will return our slice of errors in this case, not a single error. So you don't need to memorize all this, but it's super useful to look at to understand what's actually going on under the hood. The important highlights are that joining multiple errors using errors.Join gives you an error type that holds a slice of errors. Joining multiple errors using fmt.errorf also gives you a type that holds a slice of errors. And wrapping a single error with errorf gives you a more normal looking error type with a single nested error. But again, because it's wrapped, that nested error could have its own nested errors too. Okay, so now you should know how to create errors and how they are generally represented internally. So the next logical step is to actually handle those errors. So let's start with a basic function that will randomly return an error. We'll sleep for a bit so we don't get unreadable output. Make a random int. Then if that int is equal to 1, we'll return a new error using errors.new. Otherwise, we'll return nil. Then in the main function, we're going to loop a bunch of times to get a decent amount of output. And then in each iteration, we'll call basic error, and then we need to handle that error. And because this error is created with errors.new, there's no static error type that you can check against it. So the best check you can do is if error1 is not nil, then we're going to handle the error here. And in this case, I will just log it. And as a Go dev, you will 100% get super sick of typing this. One other small point is that it is very bad practice to try to check an error like this using the message. So don't do this. So now when I run this, we should get the error outputs out. Cool. So that was the most basic of basic cases. But the magic of Go error handling happens when you have actual concrete error types you can compare errors against. So the first way you could potentially check if an error is of a specific type is by just using equals equals. So say we have a Sentinel error and one custom error type that implements the error method. I'll add a function that is going to return one of those error types randomly. So we have a random int, and if it's 0, we'll return the Sentinel error. Otherwise, we'll return a new instance of the custom error type. So now we have an error coming out of our function, but we don't know what type the error is going to be. So we'll need to handle both of the cases. So in our main function, I'll do another loop for output, get the error, and let's print the error so you can see what it is. So like I said, you can try to use equals equals to check error types, but it'll only work for Sentinel errors, and it's the most naive way to do this. So I'll have more print lines. First one will be using equals equals to check against the Sentinel error. So we're going to print error equals equals Sentinel error. The second one, we'll use equals equals to check for the custom error. So we're going to do error equals equals a new instance of the custom error. And we know that comparing these two things will just straight up not work because we're putting together a new pointer to the same type, and the error is a different pointer to the same type. So this one will always be false. The only reason the Sentinel error comparison works is because you're comparing against the actual package level variable, and those two variables are the same. So when I run this, you can see when we get a custom error, the check gives us false, even though it is a custom error. And then when we get a Sentinel error, the Sentinel check with equals equals gives us true. So even though equals equals works for Sentinel errors, it's super bad practice to do that because it doesn't work with anything else. And there are tools that the standard library gives us that do work with everything else. So we'll cover those next. The first way we can check errors properly is using the errors.Is function. And for this example, we'll have the exact same setup that we did. So a Sentinel error, a custom error type, and a function that returns one or the other. We still have our equals equals checks, but now we'll do some extra checks using .is. We'll do it in a print line just like before, and we'll run errors.Is, and we're going to check the error that we got back from do something. So that's the first argument against the second argument, which will be our Sentinel error value. So just like equals equals, this will work for Sentinel errors. But this still doesn't work for the custom error type. So if we're checking against a new pointer to a custom error, we are out of luck. Doesn't work. And that's because the errors.is function generally compares by value. You can give your custom error type an is method and then have custom comparison logic, but you should just use the other functions that we're going to cover next instead. So if this is basically the same as using equals equals, what's the point? The real benefit of the is function is that it works for wrapped and joined errors. So if we wrap the error in a new error and join the error with a new error, we can check if the wrapped error contains the Sentinel error using errors.Is. And again, we pass in the error we want to check, and then the error value we want to check against. So if the error we get from do something is the Sentinel error, then this will return true. So this works. And the same is true for the joined error. So when I run this, when we get a Sentinel error, you can see that we get true for the equals equals, true for the regular is, and then true for both the wrapped and joined checks. So this is the benefit of using is instead of equals equals. It works for wrapped and joined errors where equals equals does not. One other little tidbit is that if the error you're checking against is nil, then errors.is will always return false. So you can use it as an implicit nil check if you want to. So the TLDR from this is if you are checking against a Sentinel error, use errors.Is. So that's Sentinel errors handled, but we still need to figure out how to properly check error types against a custom error. And to do that, instead of is, we'll use errors.As. So we'll take this one that doesn't work and swap out is for as. But this one works a bit different than the is function, and it gets a bit complex with the second argument. In addition to type checking your error and giving you a Boolean out, errors.As will also populate a pointer that you pass into the function with the first matching error that it finds. So we'll need a new nil pointer of the type we're looking for. And because we're following convention and using pointer instances for our errors, the error type we're looking for should also be a pointer. But to populate this variable, the function needs a pointer to it. So we end up passing a pointer to a pointer into the as function, which confused the heck out of me when I was learning. But to clarify, if we weren't following convention and using values instead of pointers, you would still pass a pointer to that value in. So the logic is the same. To populate an empty variable, you need a pointer to that variable, no matter how many pointers are in the chain. And so this will now work. And just like errors.Is, this also works with the wrapped and joined variables. So we'll bring this down here and modify it to use the custom error. So we'll use errors.As, and we need new pointers. Again, referencing those pointers. And now this should work. If we have a custom error that gets returned from do something, and then we wrap it up, we should still get true here because it matches against the actual type of custom error, not the individual error values. And the best part about this is that it extracts the error. So if P2, say, is not equal to nil, then the error matched our custom error type, and we got the P2 value populated by the errors.As function. So then we can print and use our custom data that we got from that error in the nested chain. Now, when I run this code, when we have a custom error for user 12345, you can see that we can extract it using errors.As, which returns true for that custom error. So when you're checking against Sentinel errors, use errors.Is, and when you're checking against custom errors, use errors.As. But as of February, Go has a new function that kind of replaces errors.As. This is still important to know because you'll see it everywhere, but this new one is pretty cool. Again, we're using the same setup with the Sentinel error and the custom error. And instead of using confusing pointer logic like errors.As, we are going to be using generics instead. So AsType returns two values, the extracted error, which is the first matching type in the error chain, and if an error of the matching type was found. And to actually call the function, we need to use explicit generic syntax. And then we pass in the error that we want to check. So in this case, let's check the wrapped error. And then if we actually found a matching error, then we can log this again using the extracted error. So when we run this, when we get a custom error out of our function, then AsType will find the error and we can log it. So this is way cleaner than using the empty pointer syntax. And moving forward, you should default to using this for custom error types. But again, you'll see errors.As everywhere still because this was literally just introduced. So errors.AsType, errors.As, and errors.Is are all super useful functions you'll be seeing a lot of. And they are the best practice way to check for errors. But AsType and As are also best practice when you're trying to unwrap errors or get an error from a nested error chain. But if you must, you can do manual unwrapping. And if you want to do that, there are a few things you should know. First, there's an unwrap function in the errors package, but it only supports values that were wrapped with a single nested error. So if we use error F to create a wrapped error from error 1, we can unwrap it using errors.Unwrap and pass in wrapped one. But as I said in the section covering the error type internals, the wrap error type has an unwrap method on it. So all this unwrap function does internally is type assert your wrapped error to an anonymous interface that implements the unwrap method and then calls that method. So internally, it'll look something like w1.interface. So we're asserting an anonymous interface with the unwrap method. And then if the assertion succeeded, we can call the unwrap method using the asserted value. So again, that's all this helper is doing internally. So the unwrap function is just a small shortcut, but it doesn't work at all with joined errors. And that includes errors joined using errors.Join and errors joined using error_f. And the reason it won't work on these errors is because the unwrap function expects a type that implements this anonymous interface with an unwrap method that returns a single error. But if you remember, we go back to the implementations. For a join error, unwrap returns a slice of errors. So that doesn't mesh with what the function is expecting. And the same thing is true for wrap errors that comes out of the error_f. The unwrap function returns a slice. So to unwrap these errors, you must do it with type assertion. So you have to do it the way they do it internally in the unwrap function. So I'll have an interface, okay, and then we're going to assert that J1 implements a function called unwrap that returns a slice of errors. And again, if it's okay, we can print the result of calling i2.unwrap. And then the same applies for the second joined error using error_f. So when I run this, for the single unwrap using the helper function, we get the error out. And then when we do it manually, we get the same error out. But then when we unwrap the joined errors manually, we get a slice of errors out. And again, it's usually better to just be using errors.AsType, but this is all here if you need it. Okay, next up, I want to touch on how to handle errors that pop up in deferred function calls. So let's say I have another function that returns an error. And we'll just return one using error.new. And then we have another function that will defer a call to returns error. We'll put a print line here to see what's going on. And then last in our main function, we'll call do something. So deferring this directly here is 100% a bad practice because you're implicitly ignoring the error that this function will return in a non-obvious way. So the better way to do this is to use a closure with the defer so that any errors can be propagated up to the calling function. So we'll need to return an error from do something, and the error needs to be a named return parameter. Then instead of calling it directly, we'll use a closure, get the error, and then if our error is not nil, we're going to assign error to error. And then last, we return. So if our named return parameter value was updated by the deferred function, then we'll get that value out of this function. And if the whole named parameter logic is confusing, then you can check out my video on functions in Go, and the link is in the description. Okay, next up, I want to briefly cover the gotcha that you'll hit because error is an interface. And I covered this in my interfaces video, but it's a confusing point, so I thought I'd run over it again. So let's say we have another custom error type that implements error. And we have a function that returns an error. So if I create a nil pointer to my error type here, and then return that error, when we call the function, we're expecting a nil error to pop out. And then we can check if that error is not equal to nil. So this will always be true, even though there is no real error we're returning. All we're returning is a nil pointer. But what we're really returning is an interface instance that contains a nil pointer to the myError type. And because interfaces act like a box that contains type information and value information, the actual return value is a non-nil interface with a nil value, but a non-nil type. And again, this gets confusing, so if you need to, go check out my interfaces video. But the fix is super simple for this. Instead of returning the error, we're literally just going to return nil. So now this actually is nil. And this is no longer always true. Okay, the last thing I want to cover is panicking in Go. Panics are similar to throwing and catching in other languages, but you should only use them as a last resort. In general, error handling should be done with error types. Okay, it is super easy to panic. All you have to do is use the panic function and pass a message. So this will stop the current function, run any deferred functions, unwind the call stack, and then stop the program. So anything after your panic is not executed. Now, if you want to recover from a panic, you must do it in a deferred function in the same Go routine as the panic. So we would put a defer into the boom function, and then you recover by calling recover. Super easy. And this will return either nil or the value that was passed to panic. So we can check if R is not nil, and then have our recovery logic. So now let's have a main function, and we're going to call boom. And log a recovered message. So when I run this, we'll panic here. This still never gets executed, but we recover in the deferred function, and we're able to continue execution of the main function. Yeah, so we get the recovery logic runs, and then we are recovered. Again, this is last resort. I usually only use panics when a package or function is being used incorrectly by the programmer, and you're likely to catch it in development. And that's all I got. I know it's a lot, but overall, error handling in Go is super awesome once you get to know it. Thanks a bunch for watching, and if you found this helpful, feel free to like and subscribe. As always, keep breathing, keep building, and I'll see you next time. Peace out.